Welcome back to the deep dive. Today we've built a session that's really tailored for you, the engineer or architect who has this massive responsibility of deploying high-performance AI infrastructure.
That's right.
We were going deep, really deep, into the foundation of any reliable AI cluster. We're talking about Domain 1 of the NVIDIA Certified Professional AI Infrastructure Certification, the NCP-AII.
And our focus today is systems and server bring-up.
Yeah.
This isn't just theory from a book. This is, the real-world end-to-end operational blueprint.
Exactly.
When we talk about AI infrastructure, we have to change how we think about it. It's not just a rack of computers anymore. It's more like a highly complex, synchronized AI factory.
An AI factory. I like that.
Yeah, and these systems, especially the ones with multiple high-end GPUs, NVLink, high-speed InfiniBand, they demand absolute precision. Every single component has to be there, and it has to be working in perfect, validated harmony with everything else.
And I think our mission today is to really distill that complex process. We want to give you that step-by-step knowledge an engineer has to master to take a server from, a box on the floor to a fully validated production-ready AI node. And the stakes here are just incredibly high. If you treat this initial bring-up like it's just a checklist to rush through, you're not saving time. You're actively injecting risk into the system.
You absolutely are. And that risk, it always translates into these agonizing multi-day, sometimes multi-week troubleshooting nightmares 6 months down the line when things start to get unstable.
I've been there. It's not fun.
No. It's really the difference between having a scalable, stable resource and a constant source of performance frustration. So our goal isn't just knowing the facts. It's about applied knowledge. It's about understanding with total certainty why the sequence of the bring-up matters so much.
So every step builds on the last one.
Every single step. It's a deliberate test. You use each phase to confirm that the previous components are integrated correctly and that they're free of any faults. If you try to skip right to running a huge distributed training job without verifying, say, your firmware compatibility.
Or the power supply health.
Exactly. You just lose the ability to easily trace the root cause when the system inevitably fails. It becomes a needle in a haystack.
And the moment a production system hits those performance walls or starts crashing randomly, the first place any seasoned architect looks is right back at the deployment records. Did they update the BMC? Was above 4G decoding enabled? Did they even run a burn-in?
It's the first cushion. Skipping that systematic process is, I'd say, the single biggest cause of instability in a new AI cluster. It's your initial firewall against unpredictable failure. It minimizes the time you spend trying to isolate faults later because you've already proactively eliminated the known variables.
Okay, so let's unpack this sequence. Let's start with that essential deployment blueprint that turns raw hardware into a functional, validated AI node. So topic 1.1 in the certification blueprint, it gives us this mandatory sequence. We've broken it down into what we're calling 7 foundational technical steps. This is like the universal checklist for deploying any serious GPU server, right?
It is. It doesn't matter if it's a standard OEM unit or a specialized NVIDIA HGX or DGX system.
Yeah.
This is the operational sequence that, frankly, separates a reliable deployment from just risky guesswork.
Okay, so let's walk through it. Step 1 is naturally the physical installation.
Right.
This means racking the server securely, connecting the power feeds, and we have to stress redundancy here, don't we?
Oh, absolutely. High-end systems have dual power supplies, or PSUs, and those must be connected to separate power distribution units, the PDUs.
And ideally, those PDUs are pulling from different circuits.
If you can, yes, that's for true resiliency. Then, of course, you connect the network cables, one for management and the others for your high-speed data fabric.
So once it's racked and powered, we hit step 2, the initial power on and the baseboard management controller, or BMC, configuration.
This is your lifeline. The BMC provides your out-of-band, or OOB management.
Yeah.
So you have to assign a static, non-conflicting IP address to that dedicated BMC port. And you have to do it right away.
And check the BIOS settings while you're there.
You have to. Make sure the system is set to UEFI mode. That's a requirement for any modern enterprise OS and for Secure Boot to function correctly.
Okay, that brings us to step 3, and this is the one you said separates the novices from the pros firmware updates.
It's completely non-negotiable, especially on complex HGX systems. Firmware is that low-level code running on all the different components, and it all has to be harmonized.
So we're not just talking about the main system BIOS.
No. We're talking about updating the BMC itself, the BIOS, the GPU vBIOS on each card, the NIC firmware, and on systems that have them, the really crucial NV switch firmware, and even the CPLD or FPGA firmware.
And if you skip this,
You are deliberately introducing known bugs and performance limits into your system before you've even loaded a driver. It's a recipe for these intermittent, impossible to diagnose failures.
Okay. Step 4 is the OS install. Usually a hardened Linux distro like Ubuntu Server, RHEL, or maybe the NVIDIA DGX OS.
Right. And after that, step 5 is the driver and software stack install. And the sequence here matters a lot too.
So what's the order?
First, the core NVIDIA driver, then the CUDA toolkit and libraries. Then your high-speed interconnect drivers like MLN-XOFED for InfiniBand or ROC. And then finally, any monitoring agents like NVSM or DCGM.
Got it. And that leads us to the final 2 steps, the validation phase. Step 6 is initial light validation.
You think of it as a quick health check. You run NVIDIA-SMI to make sure all the GPUs are detected. You ping other nodes and the gateway to check network connectivity. You look at sensor data, make sure baseline temps and voltages look normal. And then the grand finale, step 7, the burn-in workload. This is the ultimate litmus test. You run a multi-GPU LinPack, a heavy stressing test, or maybe a distributed training job for hours. You're checking for performance and stability under the maximum possible thermal and power load.
So the rationale behind this very specific 7-step order, that's what the exam really drills down on, right? But more importantly, it's what prevents production instability.
Exactly. It's all about systematic fault isolation. Think of it like a funnel. You start at the most fundamental physical layer and you work your way up to the most abstract software layer. If you have a bad power supply, you catch it at step 1 or 2.
Before you've even installed an OS.
Right. If you have a firmware mismatch, you catch it at step 3. You don't want to be in a situation where a GPU is throttling during a production job, and the root cause is actually an outdated BMC firmware that's messing with the fan controls. That's something you should have validated way back in step 3 or 6.
So you have to confirm the hardware is solid before you even touch the software stack. Let's ground this with a real DGX example. Racking. Say a DGX A100. It's a massive 6U server.
Huge.
You're connecting dual high-voltage power feeds. And you mentioned isolating the management plane right away.
Yes. You connect the management network cable only to that dedicated BMC port. Later, when you install the OS, you have to make sure the OS network configuration explicitly excludes that BMC interface.
Why is that so important?
It prevents IP conflicts, for one. But it also ensures your out-of-band management channel stays alive, even if the main OS network stack completely freezes or fails. It's your emergency access.
Yeah.
And it's a huge security measure.
Okay, moving on to the actual physical part of this. Topic 1.9, physical installation and safe handling. This is more than just sliding a server into Rails.
Oh, much more. Especially with components like high-end GPUs. They're sensitive, they're heavy, and they're very expensive. Safety is everything here.
So what are the rules?
Always power the system down completely. Unplug all the power cords, not just one. And you have to use ESD protection, like a grounded wrist strap, anytime you open the chassis or touch a component. Static discharge is an invisible killer for this kind of electronics.
And if you're installing a GPU yourself, maybe adding one to a system, what are the mechanics there?
First, you have to use the correct PCIe by 16 slot. The motherboard manual will tell you which one for the best bandwidth. Then you need even firm pressure along the top edge until the card is fully seated and you hear that retention clip click into place.
But you said the most common mistake isn't the seating.
No, it's power. It's almost always power. These high-power cards need 1, sometimes 2, 8-pin auxiliary PCIe power cables. If you miss even one of those, or if it's loose, the GPU just won't power up. The system will probably flag it as a critical fault, and might not even POST.
And on some of these bigger nodes, we're not just dealing with PCIe. There are other physical interconnects.
That's right. For the really high-speed GPU to GPU communication inside the node, you're installing physical ND-link bridges. And they have to be installed in a very specific topology to create that high bandwidth link. A missing bridge forces all that communication over the much slower PCIe bus, and that just cripples your intranode performance.
All this physical work leads us right to the BIOS. You mentioned a critical setting here, above 4G decoding.
Yes, this is a classic configuration trap, and you have to understand why it's there. Older systems had a 32-bit address space, meaning they could only map up to 4 gigabytes of memory-mapped I/O.
Right.
But modern GPUs with 80 gigs, 120 gigs of VRAM, they need way more address space than that to map their resources.
So if you have 8 of those GPUs in one box.
Exactly. If above 4G decoding is disabled, the system literally runs out of address space. The BIOS just can't allocate space for everything, so it starts disabling components. You might boot up, Run NVIDIA-SMI and only see 4 of your 8 GPUs, and you'll spend hours chasing driver problems when the fix is just one simple BIOS setting.
Okay, let's talk about securing this new foundation. Topic 1.3, configuring management and security. We'll start with the BMC and out-of-band management.
The BMC is, I would argue, the most vital operational component on the server. It's an independent computer, really. It's running its own little OS,
Yeah.
and it works even when the main server CPUs are off. It lets you remotely monitor sensors, power cycle the machine, access the console.
And the first step is just getting it on the network securely.
Correct. Use the dedicated OB port, give it a static IP, and critically put it on an isolated network, or VLAN. You do that for 2 reasons. First, you don't want management traffic competing with your high-speed training traffic. And second, it's a primary layer of security. Those management interfaces are way too powerful to leave exposed on the main network.
Which brings us to immediate security hardening. After setting the IP, what is the absolute first thing you do?
You change the default credentials immediately. The default admin passwords are all publicly known. It's a huge weak point. You have to use a strong, unique password, or even better, integrate the BMC with your enterprise authentication like LDAP or Active Directory.
And for system integrity, we have to talk about the hardware itself, specifically the Trusted Platform Module, or TPM.
Right, the TPM 2.0 is a dedicated crypto processor. It's basically a tamper-resistant chip that serves as the hardware root of trust. Its main job is to securely store secrets, like encryption keys, and to attest to the system's boot state.
So how does that attestation actually work? And why do we care about it during bring-up?
Okay, so during the boot process, the BIOS, the OS loader, and the kernel, they all hash themselves. And those hashes get stored in special memory inside the TPM called Platform Configuration Registers, or PCRs. The TPM can then seal an encryption key to a specific set of those PCR values.
So in a real-world AI environment, what does that let you do?
Well, first, you make sure the TPM is enabled in the BIOS. And if the server's been used before, you must clear the TPM to get rid of any old keys. But the real-world use case is TPM-backed full disk encryption. This is common on DGX-OS or RHEL. The OS uses the TPM to seal the disk encryption key.
So the disk only unlocks if nothing has been tampered with.
Exactly.
Yeah.
The disk will auto-unlock on boot only if the hardware, the BIOS, and the bootloader all match the recorded PCR values. If someone tries to mess with the BIOS or swap the bootloader, the BCRs change, the key isn't released, and your data stays secure.
Wow. That whole setup from the physical cabling to a nuanced BIOS setting like large bar all the way to cryptographic hardware like the PPM, it really shows how complex Domain 1 is.
It's all connected. And if you want domain-wise practice questions for NCP-AII, especially on these tricky areas like BIOS tuning, BMC configuration, and the security role of the TPM, FlashGenius has a dedicated learning path that focuses on exactly these concepts. It's a good way to reinforce this foundational knowledge later on.
Okay, let's move on to topic 1.4, the critical firmware update step. We mentioned this as step 3, but we need to really dig into why it's so necessary and what happens if it fails.
Right. Firmware updates are the mandatory handshake between the hardware and the software. They got bug fixes, security patches, and most importantly, these critical compatibility updates that make sure component A is talking correctly to component B. And on an HGX system, it's a big job. It affects the BMC, BIOS, GPU, VBIOS, NVSwitch, the NAC.
Let's clarify some of those. Why is something like NVSwitch or CPLD firmware so special?
Okay, so NVSwitch is NVIDIA's high-speed fabric for GPU to GPU communication inside the server. The NVSwitch firmware controls how that physical fabric works. If it's out of date, it might not support the newest NVLink protocols that the latest driver expects. The CPLD or FPGA often manages things like power sequencing and fan speed curves. If that firmware is old, it might misreport temperatures or fail to ramp up the fans when the new GPUs really need the cooling.
So there's a specific sequence you have to follow to avoid bricking components or causing these weird instabilities.
There is, and it's critical. You update the BMC first. Always.
Why the BMC first?
Because the modern tools we use to flash everything else, tools like NVIDIA's NVFU-UPD, they rely on the BMC's remote access protocols, like Redfish and IPMI. If the BMC is running ancient firmware, it might have bugs that could corrupt the BIOS flash that comes next. So update the BMC, reboot the BMC itself, then update the BIOS, and only then do you move on to the components, GPUs, NVSwitch, and NICs.
So the BMC is like the trusted delivery mechanism for all the other updates.
Exactly. You're eliminating dependencies one by one.
And this update process itself can be a great diagnostic tool, can it? Like if the VBIOS flash fails only on GPU 6 over and over.
That's a huge red flag. It tells you there might be a persistent hardware issue on that specific card, a power delivery fault, maybe a bad memory sector preventing the flash. You should immediately check the BMC's event logs with the MeTool cell list, or use NVIDIA Show Health. If an update fails, you stop. You troubleshoot that hardware, and you might have to RMA that component right then and there.
You catch a failing DIMM or a bad fan now before it causes a catastrophic failure later.
Right. We had a deployment once where a NIC firmware update kept timing out on one port. We thought it was the tool, but the logs showed tons of signal retries. The physical link was marginal. If we hadn't tried that demanding firmware update, we wouldn't have known that link was unstable until the customer tried to run high-speed traffic and saw massive packet loss. The firmware update became the diagnostic test.
Okay, let's pause and do a quick review of this core foundation before we move on to the cluster fabric.
Sounds good. So, a mini review. 3 key points here. First, the deployment sequence is rigid. Hardware-BMC-firmware-OS drivers-test. You have to resolve issues sequentially. First, the deployment sequence is rigid. Second, secure and isolate your management. Configure the BMC with a static IP on an OOB network, change the default passwords immediately, and enable TPM 2.0. First, the deployment sequence is rigid. And third, firmware has to be updated in a strict order, BMC first, then BIOS, then components, because the BMC is the modern platform for flashing everything else reliably.
A solid foundation. Okay, now let's zoom out from the single node to the entire cluster fabric. All right, so we're transitioning from validating a single server to interconnecting many of them. Topic 1.2 is all about network topologies for these AI factories. This is where a bunch of individual nodes become one single, powerful compute unit.
Exactly. The network is the nervous system of the AI factory. When you're doing distributed training, especially with large language models, you rely on operations like all reduced to exchange gradients across every GPU in the cluster.
And that needs two things at once, right? High bandwidth and low latency.
Extremely high bandwidth and ultra-low predictable latency. The network has to be non-blocking. It needs to mimic the full connectivity you have on the circuit board inside a single server.
And the architecture that delivers this at scale is the CLUS, or fat tree topology.
Correct. We use what's called a leaf spine architecture. Think of it like a city highway system designed to have no traffic jams. The leaf switches, that's your access layer, they sit at the top of the rack and connect directly to your GPU nodes. The spine switches, the core layer, they connect all the leaf switches to each other.
And how does that prevent bottlenecks?
It creates what we call high bisection bandwidth. If you imagine drawing a line that cuts your cluster in half, the links crossing that line, the spine connections, have to be able to handle full-speed traffic between those two halves at the same time.
So there are multiple paths for data to take.
Multiple equal cost paths. This allows traffic to be perfectly load balanced across that spine layer. The main goal here is a 1.1 oversubscription ratio, which basically means the network is non-blocking, no congestion.
And importantly, we're not running all our traffic over this one expensive fabric. We have to segment it.
Absolutely. The requirements for training traffic, which is RDMA, are completely incompatible with, say, management traffic. So we mandate multiple parallel fabrics.
Okay, what are they?
First, you have your training fabric. This is the dedicated high-speed InfiniBand or RoW-CE network just for GPU-to-GPU data exchange. East-west traffic. It needs special settings to make sure packets don't get dropped. Second, a storage fabric. A separate network, maybe high-speed Ethernet, just for pulling data from your parallel file system. And third, the management fabric. That isolated OOB network we talked about for BMC traffic, it should never, ever touch the RDMA network.
And in big designs like the DGX Super POD, we often see dual redundant InfiniBand fabrics, like a Fabric A and a Fabric B. What's the benefit of doubling up like that?
It's all about redundancy and capacity. Each node connects to both fabrics. So if a switch or a cable fails on Fabric A, traffic just shifts over to Fabric B instantly. And for performance, software like NCCL can actually stripe communication across both fabrics at the same time for maximum speed.
What are the most common topology mistakes you see people make that just sabotage this whole architecture?
Oh, capacity planning errors. Specifically, under subscription, someone will deploy a really high-speed switch, but they'll only provide, say, 20% of the uplinks it needs to the spine layer. So you have 8 400 gig GPUs in a node, but the leaf switch only has 400 gigs of total uplink bandwidth. That's a massive 8-to-1 bottleneck. Ouch. The other one is just cabling errors, not plugging the leaf uplinks into the spines evenly. The symmetry of the closed architecture has to be physically real. If you accidentally plug 5 uplinks into spine 1 and only 2 into spine 2, your load balancing fails, and spine 1 just becomes a huge point of congestion.
It ruins the whole equal cost path concept. So how do we check that the physical reality matches our logical plan?
We use fabric validation tools. For InfiniBand, you can use IBNet Discover or IBTopo. These tools literally draw you a map of which nodes are connected to which switch ports. For Ethernet, you use LLDP. You have to take that logical map and check it against your physical wiring diagram to make sure the symmetry and redundancy are actually there.
And that brings us right to topic 1.8, cabling and transceiver validation, the physical arteries of the cluster.
Yeah, for speeds like 100G, 200G, 400G, and beyond, your cable choice is critical, and it's completely dependent on distance. We mostly deal with 3 types.
What are they?
First, you have passive direct attached copper, or DUA cables. They're the cheapest, lowest power, but they're only good for very short distances, like 3 meters or less. They're ideal for connections inside the same rack. Second, active optical cables, or AOCs. They're good for intermediate distances, maybe up to 50 meters. They have built-in transceivers, so they're simple plug-and-play for connecting racks. And third, optical transceivers plus fiber. This is for your long runs. You use pluggable modules and separate fiber optic cables. It's the most flexible, but also the most expensive and power hungry.
So if I made a mistake and ran a 7-meter Didito cable across the aisle for my 200 gig link, what would happen?
You'd get marginal signal quality. The link might come up, but the signal-to-noise ratio would be terrible. And this is where validation is so important. You can't just check if the link is up. You have to look at the error counters.
You're talking about FEC corrections and CRC errors.
Exactly. A high count of FEC, or forward error correction, means the receiver is successfully fixing errors caused by that bad signal. But even though it's working, it's adding latency. A healthy, high-quality link should have 0, or close to 0, correctable errors.
And if the error rate is too high,
It becomes uncorrectable. You get CRC errors and the packets get dropped. That leads to retransmissions and a huge performance nosedive.
and with fiber links, you can actually measure the light signal itself.
That's Digital Diagnostic Monitoring, or DDM. It's a feature on the transceiver modules. It lets you check the transmitted and received optical power levels. If your transmitted power is strong, but the received power is weak, you know you have too much loss in the fiber, which almost always means dirty or damaged connectors.
So understanding that interplay between the physical cable, the distance, and how to interpret those error counters, that's a really complex troubleshooting skill.
It absolutely is. Knowing the theory of close is one thing, but figuring out that a specific cable is causing a latent performance problem, that takes real-world experience. You know, if you need help reinforcing tricky physical layer concepts like this, FlashGenius's Smart Review can help by giving you targeted situational explanations for these common failure modes.
Okay, let's wrap up this section with topic 1.5. Power and cooling validation. No matter how perfect your fabric is, if the system overheats or runs out of power, the whole AI factory just shuts down.
These servers demand huge amounts of sustained power. A DGX A100 can pull 6 to 7 kilowatts. It generates a ton of heat. So validation here is all about preventing 2 things: thermal throttling, which silently kills your performance, and sudden circuit trips, which cause downtime.
So let's start with power validation. How do we ensure it's resilient?
First, you have to verify the redundancy. Check that the dual PSUs are connected to 2 separate PDU feeds, an A and a B. And then you have to simulate a failure. While the system is running a heavy stress load, you physically unplug one of the PDU feeds. The system must stay online, pulling full power from the one remaining PSU without any interruption.
And during normal operation, what are we monitoring?
Load balance. Use a tool like Tool Sensor to watch the wattage drawn by each PSU. The load should be split pretty much 50-50. If there's a big imbalance, you know you have a problem. Your redundancy is compromised.
Okay, moving to cooling validation. The performance insurance policy. What are our temperature targets here?
You have to keep the GPU temperatures consistently below the throttling threshold, which is usually around 83-85 degrees Celsius. So under a full burn-in, you want to see the GPUs running comfortably in the 70s. You want at least a 10-degree safety margin.
And how do we track this?
Continuous monitoring with NVIDIA-SMI or NVSM during the stress test. If you see a GPU hitting 90 degrees, that points to a local cooling failure. A bad fan, blocked airflow. But a really critical and often overlooked check is the rack inlet temperature. If the server is pulling in air that's already warm, say over 30 degrees C, it can't cool itself effectively no matter how fast the fans spin.
And you mentioned a fan policy setting.
Yes, you have to make sure the BMC fan policy is set to performance cooling mode. You have to override any of the quieter acoustic optimized modes that might reduce the airflow you need for a sustained maximum power load.
I've seen situations where the servers at the top of the rack run way hotter than the ones at the bottom.
Now, that's a data center infrastructure problem. It means the hot air from the exhaust aisle is recirculating over the top and getting pulled back into the cold aisle. So validating cooling isn't just about the server, it's about validating the entire environment's ability to support that server under load.
Okay, let's do a quick consolidation of part 2, covering all this physical infrastructure outside the box.
All right, mini review 2, 4 points. First, your AI network topology has to be a symmetrical close or fat tree for non-blocking communication. Second, you have to segment your network traffic, dedicated RDMA for training, and separate networks for storage and secure OOB management. Second, you have to segment your network traffic. Third, your cabling choice depends strictly on distance. DICE for short, AOCs, or fiber for longer. And you have to validate the links for full speed and low error counts. Second, you have to segment your network traffic. And fourth, power validation means testing PSU redundancy. Cooling validation means running stress tests and confirming temps are stable and well below throttle points. Second, you have to segment your network traffic.
Okay, so we have a physically secure, cooled, and connected server. All the firmware is installed. Now we're jumping into the software layer. Topic 1.6 is about using the NVIDIA System Management Interface, or SMI, workflows.
Right. After you solve the driver, nvidia-smi becomes your central command line tool for configuring and monitoring your GPUs.
So what are the first few configuration steps that take the driver from just being functional to being optimized for an AI workload?
First thing, you just run nvidia-smi to confirm everything is detected and showing the correct driver and CUD versions. Next, you enable persistence mode with NVIDIA-SMI-PM1. This is a really crucial optimization, especially for shared or boosty environments.
So explain that. Why is persistence mode so important for an AI cluster?
Well, in the default mode, the driver actually unloads itself when a GPU goes idle. Then it has to reload and reinitialize when a new job starts. That process introduces a lot of latency, hundreds of milliseconds, every single time.
So if you're running thousands of short jobs.
Exactly. If you're running thousands of quick inference jobs, that overhead adds up really fast. Persistence mode just keeps the driver initialized and resident in memory, which eliminates that startup latency completely.
Okay, so after enabling persistence, we need to check the hardware interconnects that we physically installed earlier.
Absolutely. You use the command NVIDIA-SMI COPOM. This command prints out a connection matrix between all your GPUs. If your NVLink bridges are working, you should see NVIDIA tag in the output for pure GPUs.
And what if you see PX instead?
If you see PX, which stands for PCIe, where you're expecting an NVLink connection, you know instantly that the physical bridge is missing, it's faulty, or maybe the NV switch firmware config is wrong. It's a vital diagnostic.
And we can also use SMI to manage resource constraints.
You can. For a shared environment, you might set the compute mode to exclusive process to lock a GPU to a single process. And if your cooling validation showed you were running a bit hot, you can use NVIDIA-SMI-DICE-PL to set an explicit power limit in watts. It forces the GPU to operate within a safer thermal envelope, though you might give up some peak performance.
Let's do a quick troubleshooting tip. If NVIDIA-SMI fails completely or doesn't see any cards, where's the first place an engineer should look?
The kernel logs. First, check lsmod grep NVIDIA to see if the driver module is even loaded. Very often, if you have secure boot enabled but the NVIDIA driver modules weren't properly signed, the kernel will just block them from loading. You'll see those rejection messages in DMESC.
So it's a software configuration failure that stems from a hardware security setting.
Precisely.
And that leads us right into topic 1.7, comprehensive hardware validation. This is the really thorough check that's about actively testing stability, not just detection.
Right. Detection is the green light. Validation is the stress test. We have to confirm every single component is operating at its maximum rated spec and is completely error-free.
Okay, so let's run through the full inventory checklist.
For CPU and RAM, you verify you have the right core count with LCPU and the right amount of memory with DMID code. But critically, you have to run memory stress tests, like stressing, to catch marginal DIMMs. A bad DIMM is a nightmare for stability. For PCIe links, you use a detailed tool like LPI-VV. You have to verify that your GPUs and NACs are running at their full width and speed, like by 16 at speed 4.0. If a 16-lane GPU shows up as by 8, that's a huge performance bottleneck. And for storage, you check your RAID status, and you run I/O tests with FIO to make sure your disks can feed the GPUs fast enough.
And for the core AI components, we need to go beyond just basic SMI monitoring.
Yes. Here we use the NVIDIA Data Center GPU Manager, or DCGM. DCGM gives you really deep diagnostic capabilities. We'll run DCGM diagnostics at level 2 or 3. This actively stresses the GPU's memory and compute units, and simultaneously monitors for things like Shiji's errors or uncorrectable ECC counts.
What are the consequences if you ignore even a low but persistent ECC error count?
Uncorrectable ECC errors are catastrophic. They mean data in the GPU's memory has been corrupted. That will almost always cause your training job to fail, and it could even silently corrupt your model's gradients. Any component that shows non-zero persistent ECC errors, even correctable ones, has to be replaced before you go into production. DCGM is your early warning system.
Okay, this whole systematic approach ensures the hardware itself isn't the source of your failure.
It connects every single thread of the deployment process we've talked about.
Which brings us to topic 1.0, final validation for AI workloads. This is the grand finale, the last step.
This is the ultimate end-to-end performance test. We have to run a real representative AI workload to make sure the entire stack SPU, memory, NVLink, and the internode InfiniBand fabric all performs flawlessly as one unified system under maximum load.
So what specific workload do we use here, and what are the metrics that tell us we succeeded?
We usually pick a heavy multi-GPU training job, like ResNet 50 or a big transformer model, and we run it for several hours. Or we use specialized benchmarks like the NCCL all-reduced tests, which are designed to stress the interconnects to their absolute theoretical limits.
And what are the, say, 3 non-negotiable metrics we have to watch during this burn-in?
Okay, number 1, GPU utilization. It must stay near 100% across all GPUs. If it drops, it means you have a bottleneck somewhere else. CPU, storage, the data pipeline is starving the GPUs.
Clocks and thermals. The GPU clocks have to stay locked at their maximum turbo frequency. If they drop, that's a clear sign of throttling, either from heat or power. It means the validation we did in part 2 wasn't good enough. And number 3, interconnect performance. The measured NCCL bandwidth has to match the known reference values for your hardware. If scaling from 4 to 8 nodes only gives you 50% more performance, you know the problem is in your network fabric.
So this last step is the final diagnosis. It correlates any failure directly back to a specific physical error.
Absolutely. If you see thermal throttling, the fix is cooling. If you see uncorrectable ECC errors, the fix is replacing hardware. If you see poor multi-node scaling, the fix is the network. You know, for these complex scenarios that blend hardware failure and performance bottlenecks, the kind of root cause analysis you need for domain 1.10, you really have to train your intuition. FlashGenius's Smart Review feature is designed for this. It gives you targeted explanations to help you master that root cause analysis for the certification.
Okay, let's consolidate this final software and validation section.
All right, mini review 3. 3 points. First, GPU software setup uses NVIDIA-SMI. You use it to verify detection, enable persistence mode, and confirm your NVLink topology before you run any workloads. Second, hardware validation means checking all your system inventory, CPU, RAM, PCIe links, and running specialized diagnostics like DCGM to make sure all components are error-free. And third, final validation uses a heavy AI workload, like a training or NCCL test, to confirm you get sustained performance, full clock speeds without throttling, and stable scaling.
Wow. We have covered a huge amount of really detailed operational ground here. Everything from making sure a cable is seated right and securing the BMC, all the way to tuning the software stack and running these complex burn-in diagnostics.
We really covered 3 distinct stages. First, setting the management foundation, BMC, firmware, security. Second, building out the physical fabric, the close topology, cabling, power, and cooling. And third, achieving operational readiness with SMI, DCGM, and the final workload validation.
It's just so clear that building robust AI infrastructure depends on following this rigid, systematic process. No step is optional.
Precisely. The goal of Domain 1 isn't just about checking boxes, it's about ensuring every single component is signed off as stable under the absolute worst-case conditions. The systematic approach, fix every issue before you move on, is the only way to separate reliable, high-uptime AI infrastructure from that flaky hardware that constantly needs someone to intervene.
Fantastic. Now, as we wrap up, we always like to leave you with a provocative thought to think about, something that extends a bit beyond what we just discussed. We talked about how validation means setting optimal parameters, like making sure persistence mode is enabled to cut down on job start latency.
Right. And if you consider that performance overhead versus how the resources are used, the final provocative thought for you to explore is this. What is the specific risk difference in terms of job scheduling overhead and potential resource waste between setting persistence mode to enabled versus relying on the default configuration when running thousands of extremely short, bursty inference jobs on your cluster?
Think about the cost of just a few milliseconds, but scaled across a million inferences. Thank you for joining us for this deep dive into systems and server bring-up.
We hope this gave you the technical depth and the clarity you need to confidently tackle Domain 1 of your NCP-AII certification.
We'll see you next time.